Okay, so very good. So yesterday we started with the memory elements and how to build memory elements. So we went over flip-flops, static RAM, dynamic RAM, and also SSDs. And so today we need to solve this problem of access to memory by a CPU that's growing super fast in speed and memory being much slower. And today we're going to do a small experiment because I'm always puzzled in such large classes. How much are you guys actually paying attention to what we are saying? And you know, from just looking at you while speaking is not perfectly obvious. So so this time I'll be also watching you. So I'll be sitting here. Anjan will be talking about this topic of caches, and I want to understand essentially how you react to different parts of this lecture, because it's important for us to understand essentially. And I think these evaluations. I just looked at the evaluation of the course. And everything seems to be fine. I'm not concerned about the evaluations. I just don't really get a very good sense of how you guys understood this course. Do you think it's too easy, too complicated? It's too trivial. I can understand it in a matter of minutes later on by reading a book or whatever. So I just want to understand a bit better how you process these things. And so I'll leave the floor to Anjan and try to see how you react to this lecture, and yeah, let's see what happens. That's fine.
So, good afternoon again. I'm back. Yesterday you saw.
One more thing. So, sorry. So one more thing. I want to say it because I think it's really nice. So Anjan is moving on. Unfortunately, we will not have him here next year, but for a very very good reason. So he has been appointed as a professor at Northeastern University in the U.S. So.
Well, that was not expected. Okay, let's move on. So, yesterday you saw, in general, the memory technologies and how data is stored in a number of these different memory technologies. And you also saw how you evaluate memory in terms of its performance. But today we will go into it's an interesting topic of caches. How many of you know about caches? Yeah. So we'll see how it helps improve performance. What are the different architectures present, and see some sample exercises, potentially very helpful for your exam as well. So just a quick review. I know this was done yesterday. What are memories? Places where you store data. The amount of data that you store depends on what is the type of data. For example, if it's an SMS, you get about 160 bytes of data. And why do you require memory? Because not all systems require data to be stored. They cannot always keep. You need some state of memory. So you need sometimes you just need to keep the data for processing later. How can we store data? Different types of memory, as you saw yesterday. Static RAM, dynamic RAM, the good old way of flip-flops, and of course the standard storage technologies of hard disks, flash drives, etc. Static RAM, so flip-flops are the fastest. One flip-flop having 1 bit, also expansive. Building a flip-flop means, do you remember the architecture of flip-flops? You have a couple of AND gates. You So it involves a couple of transistors. So you have this feedback loop and so on. So since it involves a number of transistors for just storing 1 bit, it's expensive. And then comes in the next hierarchy, static RAM, which is relatively fast. By relative, it means it's faster than the dynamic RAM or other storage technologies. You store many more bits at the same time. Less expensive, again, relatively less expensive in terms of storage per cost per bit. So you see that about, depending on the technology, it's about 5 to 6 transistors per bit. You go further down, dynamic RAMs, much slower, and they require, of course, they are much less expensive because they require much less transistor, typically only 1. And memory is, if you remember, the memory is stored in terms of charges in the capacitor. What's the behavior of a capacitor? As time passes, the charge leaks, or the capacitor's charge leaks. So you need to recharge or refresh, which basically means that every time you do a readout, the capacitor is going to leak some charge, which basically means that you need to refresh the capacitors, which results in also slower access time. So it's slower, reading destroys content, but it's cheaper because it's just 1 transistor and a capacitor. And there are other technologies. We all know accessing hard disks, typically, especially these mechanical hard disks where you have a disk rotating, takes much longer time than flash, and then you go higher up the stack as such. So what we are going to, so in general memories, what is the behavior? You pass in a address, a number of bits address, and then you get out data. So each address corresponds to what we call as word. So it depends on the memory again. You remember byte addressable, word addressable memories. So you can address, so if it's a word addressable memory, every address corresponds to a single word, and you retrieve the corresponding amount of data. So in general, this is how computer organization. You have processor, you do, so we saw even in Verilog a couple of weeks ago how to read and how to access memory. So you have a processor accessing memory using the memory write if you want to write. And you pass an address, you pass in the data that you want to write, and then if you want to read, you read out the data. So this was very straightforward. However, until the somewhere around the 1980s, what happened was the fact that to read memory, read physical memory, you could read the physical memory in 1 clock cycle of a CPU. So it was not much of a memory bottleneck here. But however, CPU technology scaled or became much better as years passed by. We could no longer read the memory in 1 clock cycle, which means the performance of memory was improving, but not as fast as the CPUs. Of course, today you have multiple cores, so you have much more advanced architectures, but still there's this bottleneck of the memory where you can simply not access it within 1 clock cycle, which means the performance of your system was was kind of defined by the memory bottleneck. So what was so in general, what happens here is that memory system, you have to somehow, so the idea was that you want to make, at least if you're not able to scale the technology, at least try to force the memory or to force the system to kind of, fool the system to kind of look like the memory is as fast as the processor, right? Of course, the ideal memory, if you want, has to be fast. You need to be able to access within a couple of nanoseconds typically. Cheap, which means it's inexpensive. Also in terms of cost per transistor, cost per bit to store, and it's also large, so capacity. So it has to be large. So these are the 3 different characteristics we would ideally want in a memory. But we can only have 2. You cannot have everything, right? So you can either have a fast memory, which is cheap, right? in terms of number of transistors that you put in. So it's like typically they are SRAM. It's like it's not as really. It's kind of there's a balance here. So if we say you want a cheap and a large memory, then you have, of course, the standard hard disk. So if you compare, you can always come up with an example which satisfies two of them, but not everything. So what happens here is, so in general, you have this memory hierarchy. We will come back to this virtual memory later in this lecture. You typically have this hierarchy of virtual memory, main memory, and cache. So let me give you an analogy here before I go into the details. Consider that you're doing a project. You want to write a report on a particular topic. Let's assume that you don't have internet. Okay? You are still living in the era where there's no internet. So you remember there's this physical library. You know, you go to a place, and then there are these bookshelves where you can actually draw books and read, you know. So let's assume such a situation, okay? So what happens here is that you're now working on a project, but you have a computer or whatever. So now you say that I'm giving you a project in computer architecture, and you are going to fetch, or you want to go and fetch a book on a specific topic. Let's call it book 1. So you go, walk to the specific bookshelf, you pick a book 1, you come back, you refer to this book 1, write your entire project, whatever the content you want, and then you say, okay, I'm finished with this book 1, but I need some more information which is not present in this book 1. So you go back, you put back this book 1, you bring another book back to your table, you refer to this second book, you finish writing or referring to this second book, whatever you want to do, and then now you realize after you finish that you want to go back and refer to the book 1. So what do? You go back, you put the book 2 again in the shelf, bring back book 1, and you do this process again and again until you're tired, and at some point you're super frustrated, super tired. What's an efficient way of doing this? You go, you start off the same example, you go, you get up from the table, you go fetch book 1, come back, finish your stuff, but somehow you know maybe you will require book 1 at a later point in time. So you don't put back the book 1 on the shelf. You keep it, but you go back, you fetch book 2, and you come, you finish your whatever the reference that you want with the book 2, and then when you realized that you have to go back to book 1, you save the time of going and fetching back from the shelf because you have book 1 already on your table. You get the point, right? And this is pretty much how you can provide an analogy of this. So instead of virtual memory or hard disk access is very, very slow, your main memory, typically implemented using DRAM, can be considered as these bookshelves. Okay? The physical bookshelves is the main memory here, the dynamic RAM. And your table, where you kept book 1 after you finished working on it, but you assumed that you needed it later, is the cache. So your table, your work table is your cache. The bookshelf is the main memory. And what is this virtual memory? It's the hard disk. So typically in libraries, what they do is that not so much access or very rarely accessed books are kept in a basement. And you have to go call the library operator or library manager. He or she is going to say, okay, you have to go to the basement, collect it, and come back. That's your virtual memory. So those rarely accessed elements, you go straight to the hard disk and bring it back. And this is the architecture, straightforward. That's it. Simply think the entire memory system as this project, and you will never forget this at all. So technology, you have hard disk for virtual memory, DRAM for main memory, which is the bookshelf, SRAM, which is very fast, but it's expensive, which means that it's like, okay, I think this data is from probably 10 years ago. Today, the cost per gigabyte is $5,000 for an SRAM, approximately, and access time have actually gone down the picoseconds, hundreds of picoseconds. DRAM, still 100 nanoseconds of access time. So you see the key point, right? SRAM, fast access time, very expensive. DRAM, reasonably expensive, but kind of okayish, slightly slower access time, and so on. So this is the whole setup, and we need to build an organization keeping in mind somehow balancing all these three characteristics and kind of fool the entire system to, yeah.
Is there some advantage
So I think that's this is exactly what we are going to talk. Okay, that's the reason for the lecture, in fact. So when this is clear, the next couple of terms that you have to understand are temporal locality and spatial locality. Let me again go back to this example of libraries. What is a temporal locality? What you kind of assume here is that when you went back to this book 1, so you went, fetched the book 1, brought it back to the table, and you assume that since you recently used book 1, you kind of assume that in the future or in a more recent future, you will go back to book 1. So it's time. So so for example, in the terms of internet, if you looked at a web page recently, you are likely to look at it again. And that's exactly the one. You recently referred to book 1, so you're going to look at book 1 again pretty soon, or more likely to look at book 1 pretty soon. So how do you exploit? So what happens here is, how do you exploit this temporal locality is that you typically keep recently accessed data, for example, book 1, in a faster memory. So you kept book 1 in the table. That is the most recently accessed. So you keep it at memory level, which is faster for you. What is spatial locality? I said you are doing a project in computer architecture. You went to a specific bookshelf, picked a book 1. You went again, picked book 2. Potentially, since you are doing your project in computer architecture, you're going to go to the shelf that says computer architecture, or it's pretty much in the same space. So what is spatial locality is that since you used something from, exactly, if you read one page of a book, you're likely to read the nearby pages. So if you read one book from a particular shelf, you are very likely that you're going to read a book that is placed next to it. So what would make sense is that you go there, you pick up 5 or 6 books from that entire shelf and keep it on the table so that you know next time you go it's going to be there. This is it. Spatial locality, you make use of the locality in space, in physical space. Temporal locality, how recent you access, you keep it because you're most likely to access it again. Any doubts here? Yeah? Yes, this we cannot so you basically cannot predict the future, right? This is going to happen. And if this happens, it's a penalty. And we will see again how this penalty results in performance degradation. Yep? So that's why everywhere it's like likely. It's not that we accurately predict the future, but it's most likely. And you will see how when you write a typical computer program, you will end up leveraging or you end up using either data from immediate neighbors, or you will end up using the same variable, for example, again and again within a short period of time, right? So if you are, for example, I can give you two examples, right? If you initiate a variable, you're most likely going to use the variable pretty soon, right? Or in other sense, if you're going to have, so that's temporal locality. For the spatial locality, if you're going to read a bunch of data from address A to some address D, which means these data most likely are going to show, for example, if you're reading an array, they are most likely going to be stored next to each other in memory, contiguous manner, right? So if you're in a loop and you're just going to, most likely your loop increments by 1, the read memory address. So that's the most likely scenario. Of course, you will write a program which reads one from X address and one from, this is difficult to predict, right? So we can only provide an architecture for the most general use case and not for very specific. And when you write very specific programs, then you hit, that's why, so this is an interesting topic because that is why general purpose computing, it's called general purpose computing, right? These are general computer architectures. And because you typically build a computer architecture for the most generic use case. Of course, there are specific architectures which are highly performant in specific use cases. For example, GPUs, right? It's a different computer architecture, but they are specific and they are very good for doing some specific data processing because you access data in a specific pattern. So that's like specific architectures there. And these are what we are studying here is more towards general purpose computing. Does this kind of give a better overview? Good. So, let's see how we measure performance. So typical performance is measured in terms of hits and misses. A hit is basically whether the data that you are looking for has been found in the level of the memory you are looking for. If you're looking at the cache, then it's a cache hit. Miss is exactly the opposite. I don't need to explain. And there are two parameters that you typically measure. It's the hit rate and the miss rate. Hit rate is typically if you are, so how is it measured? You want to do 10,000 memory accesses, and out of these 10,000 memory accesses, 1,000 of them get hit in the cache itself. Then you say your hit rate is 1,000 by 10,000, 1,000 over 10,000. And you can also estimate the performance of memory in terms of average memory access time. And what is this formula here? So it's basically you first try to access the cache. So you remember the hierarchy: cache, main memory, virtual memory. So you first try to access the cache. So it's the time required to access the cache, followed by the miss rate in the cache, multiplied by, so if you miss in the cache, you have to go down to you have to go and look up the brilliant. So you look up the main memory. So then this is the time you require to access the main memory. And if you miss in the main memory, which is basically the miss rate of the main memory, then you go down to the actual hard disk or the virtual memory, and then it's the time required to access the virtual memory. So if you do this, you get an average memory access time of your organization, of our architecture. So a quick example, I don't think we need to go too much into detail. It's pretty straightforward. 2,000 total instructions, 1,250 of it is in the cache. So you see the hit rate is, 0.625. Yeah, sorry.
Can we give tips to the CPU, like don't do the temporal locality and spatial locality thing? We just need these data, these in the L1.
Some advanced architectures do that, but here we will not see that. But in some sense, you will have, you will see actually how a specific architecture will enable temporal locality, or is good for temporal locality, and how specific architectures are good, specific cache architectures are good for spatial locality. We will actually see that. But it really depends on what type of cache you use and the larger picture, but we will handle both.
I haven't seen this dynamically change. So typically you set the cache behavior in advance, and it behaves in that way for your architecture.
No, I meant like say specific data that you want in the cache.
Yeah, so you're talking about dynamic modifications of the changes of the cache. So you can there are ways to make sure that, for example, certain code cannot be evicted from the cache. So you can essentially execute in cache. So you can take a cache, a part of your code, a small part, and then run it in cache and force that if anyone tries to evict a line from that cache, then this. So essentially you're forcing like atomic execution of this in your cache. Or you can try to use like cache as run. But then that architecture needs to have support for that, right? So again, behaviors are typically fixed, and then there are these few things that you can do. But what you cannot do, you cannot say, well, don't use. It's not as expressive as saying don't use temporal or spatial or both, right, for my piece of data. Right? So this is.
So again, if just another example for average memory access time. So what you typically need is how fast you can access cache, how fast you can access main memory, and if we use the parameters, the miss rate of the previous example, you can kind of identify what's the average memory access time in terms of cycles. Pretty straightforward. So now you will understand how important is the cache, right? So if you go back to this average memory access time, if you have if you have your data in the cache, then you actually decrease the memory access time by 38%. 38x. So you have your performance up by 38 times. So now that somehow we have motivated that cache is actually useful to be added, let's see how and what are the different types of caches available. What is the different architecture? So in general, if you remember the pyramid again, it's at the highest level. It's the fastest possible because it's made of SRAM. Very expensive because you are able to access data fast. You need more transistors, so it's based on the memory architecture. And you also, typical cache sizes are not as big as the main memory sizes. Main memory sizes are today anywhere from 2 gigabytes to 32 gigabytes, and higher end desktop computers even go up to 64 gigabytes and so on. Typical cache sizes are anywhere between hundreds of kilobytes to few tens of megabytes. That's it. Because of the fact that you have to somehow balance the cost versus size and kind of mix and match and find that sweet spot for your architecture. So there are three different questions. Coming back to the first question that he asked, there are three questions that we need to answer in the cache design principles, right? What data to be held, right? What is the data that you want in your cache? The second is, how do we, after you store the data in your cache, how will your program or how will you find that data in the cache? Because your cache is going to have, it's not going to have the same memory address, so it's not going to have the same addressing scheme as your main memory. So we need some way to kind of find where your data is stored. And another point is that since the cache are pretty small, you're not going to load everything in the main memory into the cache. So you need somehow a way to remove data that you have already stored, which you hope that you're not going to use it in the near future. So these are the three questions which we will pretty much try to answer in this lecture as we go forward. And we will mostly focus on data reads. So what happens when you read a data. But writes are mostly following the same principle. So you can, with a bit of tweaks, but it's currently not. To understand the basic principles, this is this suffice. So what data is held in the cache? Let's try to answer this first question now, right? So cache is analogous to your table, your work table, right? And as I mentioned before, it's simply hard to predict the future. You can only leverage some kind of prediction, right? It's like really hard to correctly predict it. And which basically means that you can only use what happened in the past to say, potentially you're going to use that, exactly how the book and the project example worked. So you pretty much use leverage on temporal locality. For example, whatever you are going to whatever new data you're going to access, you pretty much have it in the cache. And you also, what you do when you, in some cache architectures, as we will see, you will not only read that specific data that you want to access, but you will also load neighboring data into your cache. So you assume somehow spatial locality in your programs, and you also load neighboring data into your cache. So this is how you decide. So you leverage the locality, temporal locality, and the spatial locality. There are some terminologies that we must be very clear before we go into the architectures of cache itself. The first thing is that capacity, how much data that can be stored in the cache. Then you have something called as a block. And what is block is that in one load, how much data you bring into the cache. And sometimes in a cache, you have a number of blocks. So you can bring, in one set, you bring in a number of, a set of data, like bytes of data. But your cache can hold a number of blocks. So you have a number of blocks definition here, which are also called as lines. So if I want to actually draw, going back to my favorite. So you have, let's assume this is going to be your cache. And this is the number of data bytes that you store is going to be my capacity. Can you see the board now? What did you do?
Press D on your laptop.
Oh, okay. Is it visible now? Okay. No answer means yes for me. So then what happens here is that, so this is the capacity of the cache, and now you can actually, in one time, you can bring in a set of data, so a number of bytes of data, which is basically I can say, every time I want to load, I bring in a block of data. However, you can actually store a number of blocks. You will see how this is going to happen. A number of blocks in what we would call as a line. Okay? So a line of cache has a number of blocks. And then you have what we call as associativity, which basically means that, I mean, it's kind of related. So, okay, and now what happens is that now this can also be called as a set, and so whenever you load data into the cache, you can store that block of data into this block, or this block, or this block. And each of these is also called as a way. Okay? So you will see as we go, you will kind of understand how each of these kind of relate to the general cache architecture. And of course, number of sets that are there. So let me push it down. So how is data found? Data is, so as I said, cache is organized as sets, and each memory address has to, so maps to one of these sets. So you saw, I drew a line, right? And that set, you have, so whenever you do a particular memory address, that can go and fit into one particular set in the cache. There are different ways in how this mapping actually happens, like how the physical address gets translated into what set or what line of the cache you want to put it in. Okay? And this is dependent on the cache architecture, if it's direct mapped, or n-way associative, or fully associative. You have a question? No. Okay. And we will actually examine exactly each of these different cache architectures with respect to a specific cache. So we will kind of assume that a cache has 8 words. Not so important. We will walk through each and every example. So just we will always have the same cache specification to walk through some examples. Okay? So direct map cache, the most easiest to understand. What happens here is that you have a bunch of physical addresses, right? Which is, say, 32 bits or 30 bits here. So you have a word main memory, and assume that the main memory is byte addressable. Okay? So, but whenever you are but the cache loads words. So whenever you read a particular value, you read the entire word and put it into the cache. So now what happens here is that you choose some bits of your main memory, the addresses of the main memory, and map those 3 bits directly into the cache address lines. Okay? In this specific case, the cache has 8 different lines. So you can store data in any one of these 8 caches. But for a direct mapped cache, which physical main memory data goes into which of these set numbers depends on any 3 bits. Because it's an 8 set cache, you will depend on any 3 of these main memory addresses. So for example, if I want to choose 4, 24, and E4 as shown in the example, you see that all these 3 address space actually have their these 3 bits, 0, 0, 1, which means that they map to the first set of your direct map cache. What this means is that all these 3 addresses, if you are going to read this, followed by 24, followed by E4, they all will have to go into the same line, which means if you are reading it in sequence, one has to be removed, so you are always going to constantly be removing the data from the cache. But if you are going to read from this, so from 4, followed by 8, followed by C, what happens here is that the cache address lines are mapped as 001, 010, and 011. So basically what will happen is that this particular word will go into the first one, followed by 8 going into the second cache set, 3rd going into the 3rd cache set. That's it. And there is no need for removing data here. And this is direct map cache. So you have extremely simple way of addressing your cache line. And yeah, so basically you have a very simple mechanism of it. But there are some disadvantages. We will see what happens here. Any questions till now? Yeah?
How do you know if the address in the cache to what of them?
Sorry?
The cache refers to?
So,
If 001
mm-hmm.
refers to 04 or to 20?
No, it's the other way around. So it's not about 04. So you have, it's the other way. This is the address of the main memory. If you are going to load, I'll show you with an example. That's easier. Okay? But we will finish with an example, and then we'll come back to your question. Yeah?
I guess it's sort of the same question, but a few slides ago it was mentioned that we can load and store to the cache line.
Mm-hmm.
So, and I guess if we store something to the cache, it will propagate down to main memory.
Yes.
And right now,
We only store load. That's why I said we will consider only load, because writing down involves a little bit of slightly more complicated write backs, and depending on, again, the type of cache architecture, you wait until you write back and things like that. We don't want to go down that advanced cache architecture. I mean, it's not advanced, but I think the basic principle is the same. So that's why we look into cache loads for now. Because, let me give you an example. The simplest cache architecture, if you want to write back, it's called the write-through cache. Okay? What that means is that you write into the cache, it goes straight into the memory also. But there are some more advanced mechanism of cache handling, which is you only write after some time. So you write first to the cache, because potentially you're going to write again and again into the same variable, so you don't want to keep accessing the main memory and keep writing to the main memory. So you're potentially going to wait and then write after later some. So there are these other mechanisms to write through.
So there's also another.
Yeah, sure.
There's also another thing that you can.
You have to switch it on.
Okay. So there's also another thing that you can think about. So there are actually even more complicated cache architectures, because each of the, if you take now, of course I should write somewhere where there is light. So if you have a multi-core architecture where each of the cores potentially has its own L1 and L2 cache, right? So each one of the cores might have L1 and L2 cache, which are essentially 2 levels of cache, right? The smaller cache and then the bigger cache, which for each other they behave in the same way like cache and memory, right? So you have this hierarchy. Then you might also have an L3 cache, which is shared between these, and it's essentially all-inclusive cache, which means that whatever is in L1 and whatever is in L2 is also in L3. And then you have to wait essentially until all of this is propagated and so on. But then there are also, in some architecture, there are also interesting behaviors where, for example, if something is evicted from one of these caches, it shouldn't be evicted from L3 if it's in use by another core. So there are much more complex behaviors that one could consider there, and I guess this is just an introduction to caches, and then one can go on. Yeah.
And to kind of continue along the same path, if you have multiple cores and multiple caches, there are also protocols that run on top of these systems to have coherence between these caches. So you have cache coherence protocols, and then you have multiple. So you can go as advanced as possible in just caches. So this is just to get you started, and it's a very good thing that we are already talking about cache coherence protocols now. So let me push it down again. So how does the direct map cache architecture work? As I said, you have the memory address there. The memory address is split up into a tag, a set, and the set is basically the number of bits you have, number of sets you have in the cache line for a direct map cache. So you have 3 bits here. This is good. So you have 3 bits addressing all the 8 set of the cache, and you have a byte offset, which basically means that if you want to access a specific byte, you need to use this byte offset because your cache is going to give a word. And then it's very simple. You have the tag part of the memory address. You compare it with the tag that you store, the tag address that you store in your cache line. If it's equal and if it matches what you call as a valid bit, because when you store a data and that data is valid, you set a bit 0 or 1. So if it's 1, it's valid. And if it's actually valid and the data and the tag matches, you generate a hit, and then you don't have to go down to the main memory to access. So a quick overview using an example. Maybe this clarifies some more questions. So consider this assembly code. You basically do this loop 5 times. You try to access data from addresses 4, C, and 8 5 different times. So what's happening now is that 4, if you remember the direct map, your 4 is going to map to set 1, C maps to 8 maps to set 2, C will map to set 3. There is no conflict of addresses. So you are going to store all the 3 in 3 different sets of the cache. So and then when you continue to do this loop, what's going to happen? Only in the first loop, you're going to get cache miss, right? So once you have your data into the cache, the following loops, you're not going to load it from the main memory because your cache is going to generate a hit. What is the miss rate? Miss rate is basically you have 3 memory accesses, 5 loop iterations, 15 total memory accesses, out of which 3 you will have a cache miss. Once you load it into the cache, you're not going to have a cache miss, which basically means that your miss rate is about 20%. Here, one important thing that we would want to, one terminology that I want to introduce here is compulsory misses. What is a compulsory miss? Here, it means that you really don't have that particular data. It's the first time you are starting up. All cache lines are empty. So you have to load whatever data you're going to, whatever address you're going to read into the cache. And this is going to be a compulsory cache load. So which will generate a compulsory miss. And this is a compulsory miss. Let me quickly show another example, and then we can go for a break. So you have the same example of 5 iterations, but this time you access memory address 4 and 24. Remember, 4 and 24 mapped to the same cache set, which basically means that when you load 4, you're going to generate a cache miss. You read it and load it into this line. But then when you're going to try to when you try to read from address 24, it's going to be a cache miss. You will try to load it from the main memory, and you will put it back again into the same cache line, which means you will remove the 4, the data from the address 4, which basically means that all your memory accesses is going to result in a cache miss. You got the point, right? Exactly. So it's like this type of misses is called conflict misses, which basically means that whenever you are reading a new memory address, you're always storing it in the same cache set, which means you're always replacing the cache set. You are actually not using the cache is not helping here. Basically, you're always reading from the main memory. With this, we will go for a break, and when we come back, we will look at n-way set associative cache. So let's continue. We talked about direct map cache, and that was one specific architecture. Now we continue with n-way set associative cache. In some sense, what I can say is that if for set associative cache, it's kind of like the parking lot scenarios, right? So assume that you have for this group of people or for the number of employees in ETH cannot have as many parking slots. So they have to do some kind of sharing, right? And this is pretty much how caches are also going, because cache is much smaller than the main memory. You have to do some form of address translation, right? And how this happens for a direct map cache is that, to give a pretty straightforward example, you have your ETH student ID, and assume that depending on some specific number, you have to go to that parking slot. That's it. Like last number of your ETH number ID, you always go to that parking slot. That's it. And if there are more than one person with the same parking slot and the parking slot is full, then you don't have an option. And it's exactly the same thing. I mean, it's pretty much the same way this is set associative cache is also organized, except that if your address has a specific set value, you don't have only one place to go, but you have multiple places to go. So you have multiple ways in which your data. So you have, in this specific example, you have two different ways. So for a specific set address or a set value here, you can go to either way 1 or way 2. So you kind of add some performance to the system. So a question actually that arose in the break is that why is this set 3-bit close to the least significant bit? Why can't it be close to the most significant bit? So why? Is there a reason for it? Yeah. Exactly, because the higher you set your set values, the higher bits. If you are choosing higher end bits, then when you're reading addresses from consecutive memories, your end the higher order addresses are going to be the same, right? And that's why you kind of choose something that is much closer to the LSB. Okay, so in a set associated cache, pretty much the same division. You have memory address, which is separated into tag, set, and byte offset. You have here instead of, so assume that the cache is pretty much the same capacity. So you have 8 cache, 8 blocks of data that you can store in this cache. But now it's a 2-way set associative cache, which basically means that in one single set, you can store two blocks of data, which reduces the number of sets in the cache to 4, that's why you have this difference out here. So when you're actually, so in general, when you're going to read from a specific address, you choose, so you have the tag that goes into your way, and then depending on the set, you can actually pick from both. You pick from both the ways, so you read data out from both the ways. But depending on which of it is valid and which tag matches, you can choose either the first way or the 0 way or the way 1, and then you get appropriate data. Understandable? Yeah. So going back to this example, so what happens here is that you remember you had a 100% miss rate, right? Which basically means that you have this example where you have 5 code iterations, you're reading data from addresses 4 and 24, and in a 2-way set associative cache, both 4 and 24 is going to map to the same set, right? So but you have 2 ways here. So the first one goes into, let's say the first one goes into way 0, and the second address goes into way 1, which basically means that when you are going to read in the second loop, you already have the data in the cache, and you're not going to have the miss. So you reduce the miss rate from 100% to 20%. Simple, right? So in general, associativity reduces all these conflict misses, okay? And of course, you have the fully associative cache, which is basically no conflict misses. So you are never going to get any conflict misses. And in some sense, in terms of the parking lot scenario, it's just that you can go wherever you want. You can park in wherever slot you want. So that's pretty much it. You have one big cache set, and any data can actually be stored in any of these ways. And of course, it's expensive to build. Typically, you don't get fully associative caches. Any questions till now? Good. So how do we actually handle spatial locality? So in terms of spatial locality, what you can do is, so we always saw block size 1. Now, what we are going to do is, what is spatial locality? If you remember it, if you remember, you actually read memory, you read data from consecutive memory addresses. So instead of reading just one block, you are going to read a number of blocks at the same time. And thus, if you increase the block size of your cache, you can potentially leverage or increase the performance of programs that require the spatial locality. So let's go back. So you have this change in the cache architecture. We make some changes in the cache architecture, which is you have the block size of, so from B equals 1 word, you increase it to 4, but you still keep the 8-word cache limit. And what happens to this to the architecture is the following. You no longer, so one modification you do to the memory address is that in addition to the tag, set, and byte offset, you also have a block offset. So you just want, so in order to choose which block the data belongs to. So if we are going to now read a specific address, what's going to happen is that you're not just going to read that address or that block, but you're going to also fetch, the cache is also going to fetch neighboring address space and store it in your cache. So you have here, specifically in this particular example, you have only 2 sets because each set already stores 4 blocks. Okay, so each set stores 4 blocks, and whenever you are requesting a specific address, you also request the neighboring 3, and then you put it in, you store it into your cache line, and then when you set the valid bit, and when you want to read, you have the same principle of tag matching. You use, but here instead of the set directly matching to a particular set line, you have the block offset, which is basically choosing which block or which way you want to choose, and then you simply read out the data. So in this specific, in this example, how do you actually improve the performance? So going back to this example of 5 iterations, 3 different reads from addresses. Now, if you see here, 4, C, and 8 are all going to go into the same line, into the same set, which basically means that you are going to, so you don't have a cache, you only have one cache miss. So when you read, or when you try to access 4, you also access the neighboring blocks. So you have already filled up your cache set with 8 and C. So basically your miss rate reduces to much lesser value. So but this is, in some sense, this is a direct mapped cache, right? So you have specific addresses. Instead of having a set address directly mapping to your set, the line of the cache, you have a specific block offset, which matches to the block of the cache line, and then you have all the contiguous data into your cache, so you reduce your miss rate dramatically. Good. So to recap cache organization as such, you So what we did is this. So we saw direct map. You have only one way where you can store your data, and the number of sets is equal to the number of blocks, because you have one block per set. And then you go down. So we looked at n-way set associative cache, where you have more than one place in the same set where you can store the data. And of course, fully associative is that you store your data, or you read from, so you store your data in the cache in any of the given ways there. So your number of ways is equal to the number of blocks. And there's only one set. So this is the kind of comparison between blocks and sets and ways. Okay? So one thing that we didn't cover is capacity misses. So capacity misses, so basically caches are small in size, which basically means that whenever they are full, they have to be, so some line has to be, so some data has to be evicted irrespective of the type of cache architecture. And this is called a capacity miss, which means that that particular set is already full. You have to replace it, and you have to follow, in some sense, in some specific, you have to kind of have a specific way in which you can replace. So in a direct map cache, this is simple as well, because you only have one place where the specific address can go. So there's only one place to put it. You have to replace it, no other go. So it's kind of easier. In associative cache, you have multiple ways depending on where you have to go. So if all the blocks are filled, then you have to choose which way you want to store your data and which way you remove it. And typically, there are a lot of mechanisms in which this is done, but typically what's followed is the least recently used. So out of all the 4 ways in which, or for example, if it's a 2-way set associative cache, if you are going to access one, so the least recently used way is going to be removed. As simple as that. So to just kind of summarize the type of misses, you have compulsory misses, which is basically you need that first load into the cache. You really cannot do anything better than that. You will have a compulsory miss. And then capacity miss is basically when all the different ways are full, you have to replace it, so it's a capacity miss there. Conflict miss, you have the same data that is mapped into the same cache set, which means there's a conflict, so you have a conflict miss. And miss penalty is basically whenever there is a cache miss, the extra time that you need to access data from the main memory is what we call as the miss penalty. How does least recently used work? It's the same kind of example. You have 4, 24, 54, 3 different addresses. You have, first when you load 4 and 24, you put them in, this is a 2-way set associative cache. You load it into one of the, you choose a set, you load it into one of the 2 ways. So you put it into the way 04, 24 in way 1. When you want to replace it 54, you choose 4 because that's the most recently used. So that kind of comes almost to the end of caches. And so, in general, to summarize caching itself, we wanted to answer 3 questions. What data needs to be stored in the cache, which is basically leveraging these 2 locality principles of temporal as well as spatial data. How data is found in the cache, because when you read data, so the address of the memory doesn't match the address of the cache lines. So how data is found depends on the set. We have 3 different cache architectures, such as direct mapped, set associative, and fully associative. How data is replaced, typically we use least recently used. And data replacement is more important for n-way set associative cache because you have more than one way to put the data, so you need to figure out which one to remove first, and typically least recently used is the way we go. Yeah? Sorry?
The V bit.
The valid bit, yeah.
Valid bit. Yeah, is it used to say if it's valid to override it, or?
Yes, in one sense, it's also used to say if the data is actually, yeah, you can use the freeze part. In some more advanced architectures, it is also, I mean, not just advanced architecture, but when the data has changed in the main memory, then the cache has to be informed that whatever data that is actually stored in the cache is no longer valid. And this needs to be also set back. So instead of removing the entire data, you just flip the bit. And it just increases performance. In more advanced architectures, this is also used for making sure that all the caches have the same data and so on. Okay, so in general, if you see the type of the size of the cache and how the cache misses occur, you see increasing cache sizes, you in fact bring down the capacity misses because you have more space to store. And if you have more associativity, which basically means that you have more than one way to store the memory in the same set, then of course you reduce the conflict misses. You wanted to say something?
Yeah. So before we switch to other topics, so I mean, caches are interesting for many reasons, right? I mean, also for my favorite topic, for security reasons. So one of the things that you probably noticed by now is that caches are shared by many applications, right? And you can see it conceptually as, you know, if you know that a certain application is running, you know that some data related to that application that is important for that application has been loaded into a cache, right? So you know that, right? And now what you can do, you can devise a test as so let's say that you have some data is in the memory and some data here is in the cache. And now if the application 1 is running, you know that some data of application 1 will fill this cache. So all of this will be application 1 data. And you know that, and some of the other data from application 1 will be stored in the memory. Now if you see this as an observation, if you know the behavior of application 1, what you can now do is now you can try to test whether something was loaded in the cache or if something was loaded in the memory. Now, how would you do that? Well, you can start playing with this application by, if you are in application number 2, you can now, for example, you can now start reading from the memory, which will cause evictions from the cache of some of the cache lines of application 1. And then you can measure the time that it takes application 1 to execute certain operations. So, for example, some cryptographic operations. And this will give you enough power. Now you will know, for example, because if application 1 goes to memory and fetches data, it takes time t, right? If it goes to the cache and fetches data, it takes some time t, which is necessarily smaller than t, right? This means that if something is in a cache, this will run faster. If it's in memory, it will run slower. And using this, you can actually break encryption schemes and you can leak information from application 1 to application 2. So caches are actually really interesting examples of a common resource. Obviously, memory is also a common resource, but these are two common resources, right, that are accessed by two potentially adversarial processes. And now, and they can be distinguished in terms of the access time. And this thing actually really works. It even works over a network. So You can break things like AES, Advanced Encryption Standard, and similar schemes by leveraging these kind of observations. So this is just a side. Yep.
So how do you prevent that?
You can't. I mean, that's the beauty of security. You know, some things are just as they are. You know, due to the computer architecture, you cannot prevent it. Even the most recent Intel's security extension called SGX, I think I mentioned it last time as well, actually is vulnerable to these kind of cache timing attacks. Now, the way that you can actually prevent it is that you need to write code that is resilient to this kind of attacks. But then, of course, you can write libraries that do crypto operations that don't leak. Right? For example, you can flush the cache after every operation that you do, right? But then the problem is, first, you get a performance hit. And second, if you have any kind of generic computation that you do, you would need to rewrite your code in order to make it, you know, leakage resilient. And that's a lot of work, and typically people will not do that. So some of the vulnerabilities still remain. Yes?
Could you put some kind of MMU for the cache so that different applications can't use the same cache addresses? Or?
Yeah, I mean, you could. So essentially, that's what they do for memory, right? If you would do the same for. So if you take a memory management unit, right, as your colleague is mentioning, that would handle somehow access rights of different applications to the memory, and this memory management unit is configured by the operating system. Now, doing the same for cache would mean that you would be able to reconfigure the cache and split it into pieces and have essentially isolated caches per applications. Now, this again would have a pretty high performance hit, right? I mean, for applications. And honestly, I don't know how efficient could that be done in hardware as well, adding another unit, because it would need to sit next to in the processor, because these caches are in the processor as opposed to the MMU, which sits outside, right? So that, I don't know technologically how fast or performant this would be, but in principle, I guess if your caches are large enough, you could do that, right? Other questions or?
Yeah, so could the memory management unit not have like a bit for safety?
So the only thing that you can do is you can essentially force that. I mentioned this before, that while you run a certain process, no evictions can happen from a cache. And if they happen, you abort the process. There is an interrupt, and you abort the process. This is one. This is essentially transactional memory, and Intel implements this, and so you can do that. And now you can use this mechanism in order to somehow to lock an execution and to have it fast, because you can say, now, while I'm running, this cache is mine, in some sense, right? So that you can do, but of course then the amount of memory that you can somehow lock there is the size of the cache, which might be quite small, so you're still somehow restricted within the size of the cache. So you would need to take your application, break it into small chunks that are kind of that are small enough to fit within that memory, and then you can do something, right? But there is no explicit other mechanisms that, well, there are some other tricks and so forth in some more specialized architectures, but yeah. But maybe this gives you an idea of the complexity of this space, because it's not only, so you have to take into account this whole hierarchies of caches, multiple cores, these kind of security aspects that you might care about in different applications, and now you see why, for example, the complexity of this design of computer architecture is so high, right? Because it's a really multidimensional optimization process, right, that you have to do. Okay.
So to continue, continue on the multi-level caches. So till now we looked only at this one cache architecture, but however in practice you have much, so here many more levels of cache. You have, as Sachin mentioned, you have L3, L1, L2, and the fundamental idea here is that the larger the cache, the more expensive it's also going to be, but also it's going to have a lower miss rate, but also longer access time. So you somehow try to balance all these factors, and you have L1 cache, which is the closest to your CPU, L2, and then L3 typically. And as you also see that L1 is also the smallest. You have typically a few kilobytes, and then you go higher down until memory. So till now we were looking at the physical memory or the main memory, but we also had this virtual memory, right? So to give some kind of quick feel about what is virtual memory and how this is fitting into the big scheme of things, basically what's virtual memory is that you somehow give the illusion or to the system that you are actually having much more memory than than the physical memory. And what happens, so in some sense, we could see the main memory, that is your RAM, as some form of cache for your hard disk, right? That's it. So you have cache for your main memory, and then main memory is actually some form of cache for your virtual memory. And pretty much, if you go back to this hierarchy, you have virtual memory, which is right at the bottom, very high capacity, cheap as well. So I don't have to tell you what a hard disk is. So what is basically, in some sense, what's virtual memory is that you have multiple programs running in your system, and each of these programs uses what you call as virtual address. And these virtual addresses that you're referring to actually map or are actually stored on the hard disk, and a small subset of these virtual addresses, of the entire space of addresses that belong to the hard disk, are stored in your main memory. So DRAM is the main memory here. And to kind of go further up the ladder, a smaller portion of the main memory is actually stored in the cache. So that's the whole memory hierarchy. And if we look at the virtual address and the address of the main memory itself, they do not match, so there needs to be some kind of a translation process. So you need exactly how we had the translation from main memory address to cache sets. You need some form of translation from the virtual memory address, which kind of maps to the entire hard disk space, to your main memory address space. And also, so one more important thing is that each program that runs has its own virtual space typically, and this is also useful for memory protection, as Sachin mentioned here before. Security is for security purposes, so that you can actually secure different programs from not accessing each other. So they run in their own virtual space, which basically means that they don't have to be aware. So one program need not be aware of another program that is running. So they don't have to access, or they are not allowed to corrupt the memory that is being accessed by another application and so on. However, if you look in the security aspect of things, a whole bunch of exploits have been done exactly using this space. So one memory, one application, a malicious application, trying to corrupt access of another, access of the address space of another application, and so on. So to give you some exact kind of analogs, so you have caches, blocks. The same thing is called a page in virtual memory. The block size is called the page size in virtual memory, and so on. So except that you don't have a cache miss anymore, you have a page fault. And this is pretty much the analog of cache terminology versus virtual memory terminologies. So page size, we all know what page size is. So just it's like block size. So it's the amount of data that you read into the cache. Here it is the amount of data that you read into the main memory. Address translation, what physical address in the main memory maps to which virtual address in the hard disk. Of course, this address translation needs to happen somewhere. So you have a page table, which is basically a lookup table which has the mapping of this physical address, which directly maps to the physical, the main memory or the physical memory, and then you have the virtual address which has the address space. So this is kind of a high-level overview of how things happen. You have the virtual address space. They map to the hard disk, and also you have a mapping into the physical memory address space. So most of the accesses, if you want a very performant system, most of the accesses when you do on the virtual addresses would already be there in the physical in the main memory. So you will have a hit from the virtual address to the physical address space. Exactly. And so let's see how this whole address translation happens. So you have this is very similar to the cache address space, right? Instead of having tags, sets, and block offsets, you have the virtual address is divided into the virtual page number and a page offset. And this virtual page number undergoes the translation process, which maps to the physical page number, which is in the main memory. And so basically, the translation is because you have much smaller physical memory, and this seems like just 4 bits, but remember that it's 2 power 4 bits, so you have almost 1/16. So your virtual address space is, in this particular example, 16 times bigger than your physical address space. Okay, and it's pretty much the same. You have the virtual page number undergoes a translation, and then you have a physical page number. The page offset indicates the exact physical address so that you can fetch this from the main memory directly. So a quick example here, you have virtual memory size which is 2 gigabytes. You can think of it as, let's say, a hard disk space, for example. And then you have but the physical memory or the RAM itself is just 128 MB, which is unheard of today. And then you have a page size which is typically 4 kilobytes. And every time you read from when a program fetches, it fetches this 4 kilobytes of data into the main memory, and then the translation happens. So if you exactly convert this system example into a much more detailed thing, you will actually end up seeing that you have a virtual address of 31 bits, 27 bits, and so on. So I don't think we need to go into too much details here because it's kind of self-explanatory and you can actually walk through it yourself. So this is exactly what I was telling. You have this is the physical memory. That's the memory that we were talking about. I mapped to a much larger virtual memory or virtual address space. And you have a physical page number mapped to a virtual page number, and you see that you can actually see that multiple virtual addresses can actually map to the same physical address, pretty much exactly like how caches work. So you can actually map the cache mechanisms to how virtual address and physical addresses behave. So one thing that I would like to kind of spend a little bit time is the translation, but again, it's very similar to how the caches work. So you have a page table, which is fundamentally it's a lookup table between the virtual address space and the physical address space. You have the valid bit and the physical page number. So if you look at this page table example, this is the physical address, that's the main memory address, and then you have the virtual address, which you have some portions of, so you have the higher order bits indicating the page number. Here in this specific example, it's 2, so you go to the second, 0, 1, 2, so the second entry in the page table. Inside the page table, you have the physical page number, so you take it out, and you also have the page offset in the virtual address, so the effective physical address is going to be the following. Very straightforward again. So again, walkthrough example of 5F20. What happens here? You have 5F20, 5 entry, 5th table. So you have the number out, and then the offset is the page offset here maps to 001F20. It's again self-explanatory. I'm skipping these examples. So one big challenge out here is that this page table is large and is typically stored in the physical memory, which basically means that every time you want to read a particular address, you have to go all the way down to the main memory instead of the cache, right? So you typically have this whole mechanism because cache, main memory, virtual memory, and here the page table is always located in the main memory. And which basically means that every time you're going to do a load or a store, you have to do 2 main memory accesses. So you have to go down, look for the translation, get back, access the data, get back. So it kind of affects performance. So what is typically done is we have there is a translation look-aside buffer. Now, translation look-aside buffer is kind of a cache for the page table. Okay, so you kind of store. So you have the most recently used translations which are present in the page table. You kind of store it in this translation look-aside buffer, which basically means that whenever you are going to, so you don't have to go you don't have to make 2 main memory accesses. This translation look-aside buffer is it's a small memory, typically an SRAM. Also, fully associative. So any page table entry can go into any of the available ways. So, and it's extremely fast. So you save that 1 extra memory access that you have to do if you don't have such a TLB. Okay? And typically all these things are managed in some sense by a memory management unit, but we don't go down that path now. So yeah, well, I already mentioned it. It's accessed within 1 cycle, very small. So you only can store 16 of the entire set of page table entries that are there. It's fully associative, so there is no mapping that you require anything. You have to go through the entire search space and get your entry out. So it's typically has a 100% hit rate. So it really improves this by putting in this extra translation look-aside buffer, which is basically a cache for the page table. You actually improve performance of your system dramatically. I don't think, so it's again a straightforward example. It's easy to walk through. I would not go into details. If you have any questions, you can ask later through email or you can drop by. But it's very straightforward, standard, just like the caches, basically. We already talked about memory protection even before we came to this slide. Yeah.
I have a question. Instead of the TLB, can't we have a small processor on the DRAM, and then when we go there and we ask, as soon as we get the physical page, we ask again, instead of going back to the CPU, we go to the small processor and then it gets the real.
Well, it adds complexity because memories follow a pattern. It's super easy. The cost of memory manufacturing goes down because there is a pattern. Because you have, for 1 bit, you have exactly that same pattern of transistors and capacitors. But now you say you put a processor. You guys already finished designing a CPU in the labs, right? So you say you put a processor, which is not the 32-bit processor that you designed, probably you might have a much simpler one, into this memory. You're going to increase the complexity, you're going to increase the cost, and I don't think your performance versus cost is going to be so much there. You're going to really increase your memory manufacturing cost there. Because typically patterns means you don't have to, patterns reduces cost. It's as simple as that. So we already talked about memory protection. So again, skip. Virtual memory. So to summarize, increasing the capacity. Virtual memory is the slowest. The accessing the hard disk is the slowest. However, it gives you the illusion of accessing much larger address space to the CPU, and your main memory is a kind of a cache for your virtual memory. And this translation between main memory, which is physical, which is also called as physical memory, and the address space in the virtual memory uses a page table. But page table is big, so you cannot store page table directly in the cache. So you, instead of avoiding main memory access, you have something smaller, which is called the translation look-aside buffer, which is acting like a cache for the page table itself, and pretty much you go up the ladder like that. So this is the entire memory organization of the system. And this brings me to the end of the lecture, 4 minutes early. I think we can stop here. Thank you very much.